It will be just a tentative explanation of the connection between Liouville quantum gravity, Gaussian multiplicative chaos in planar maps. So this is all about conjecture made by physicists about this relation, and well, I'm just trying to explain. So there will be no proof or no something correct. Okay, I'm just trying to explain you why we are doing this. Okay, so well, the first historically, why do you consider Liouville quantum gravity? So maybe I should first try to explain the concept of the notion of action in physics. So let's start with a very simple example. You take a functional on R, and say a very simple functional. Okay. So this is a very nice function. Looks like this. You have a minimum at 0. And now, how do you construct a probability measure out of this? You choose a parameter beta, which plays the role of inverse temperature. And you consider exponential minus beta h. And you integrate this weight with respect to the uniform measure on R. Okay? You get a probability measure up to a normalization, which is a Gaussian random variable. Okay? And depending on the temperature beta, you change the variance of your Gaussian. Okay? So this means that changing the variance means that you have a random law which is distributed, which is centered at your minimum, and depending on the temperature, it is more or less spread over R. Okay? So H in physics, it's called an action. Okay? It plays the role of a weight that you put on the configuration X. Okay? So now you want to play the same game, but instead of having real numbers, you want to have functions. Okay? Functions which are defined on R. So now if you look at so I want to construct an action which is called the Einstein-Hilbert action. And this will play the role of my H here, but this will be the action of gravity. Well, so this action is given by A of G. I'm going to explain the notation. So here you have, say M is a topological surface. And in what I'm going to talk about, this will be more or less the topology of the sphere. G is a metric on M. And when you have a metric, you can define something which is called the Ricci scalar curvature. Whatever the definition of the Ricci scalar curvature, you will see that we don't need the definition in what follows. This is the main, the fact that we don't need this term here is the main motivation for considering 2D quantum gravity. And lambda G is the volume form of G. Okay. So here, this is just the total integration of the curvature with respect to the metric, the volume form of the metric. And here, this is just the weight, the volume the volume of M. Okay, this is the volume of your wall surface. This is the Einstein-Hilbert action, and what you want to do is to construct a random metric this way. So A is my action, and you want formally to construct a random metric on M by taking the exponential of your action and integrating with respect to a formal measure on all the possible metrics. Okay, so this is pretty much the same picture as here, but here you have a random metric on G. This is called well, quantum gravity. Well, now, well, you know, maybe you know that in physics we are pretty much interested in 4G gravity because you have 3 dimensions for space and 1 for time. Okay, but here we deal with so there is no time in what I'm telling you, because basically the idea is that if you deal with a metric in space, you should have something. This is a Lorentz metric in quantum gravity. Okay, and you have minus t squared here. Okay, so physicists say that you can make an analytic continuation in t to change the minus here into a plus. Okay, this is called when you've done this transformation, you talk about Euclidean quantum gravity. You don't care about the Lorentzian metric. Okay, so this is well, this is some motivation for considering Euclidean quantum gravity. Though these metrics are with a 2 plus signature. I mean, there are only plus in my metrics. And well, the second thing, why do we consider only 2D quantum gravity? Basically because this term here in the action, in 2D only, it is only topological. Okay, you have a theorem called Gauss-Bonnet, which tells you that this term only depends on the topology of the surface. Okay, this is you have the Gauss-Bonnet theorem, which tells you that this integral here is equal to 8 pi times 1 minus chi, well, where this parameter here is just topological. This is the Euler characteristic of your, well, say constant chi is equal to 0 on the sphere. Okay, so this term, which is rather complicated in 4D, disappears in 2D, and this is why quantum gravity is pretty much convenient in 2D. Okay, and so we expect that this term is completely trivial. Okay, we expect that this theory is rich enough to be interesting. Okay, so so now the thing is that well, you want to have an insight of the shape of your metric G. Okay, so basically, if you take a metric on the sphere, it is well, say conformally equivalent to some fixed metric on the sphere. Say you can fix a G hat, your favorite metric, on the sphere. And here, if you have fixed G hat, this is a reference metric. All the other metrics that you get up to a conformal transformation are given by the exponential of some function phi. Okay. And the thing is that since G hat is fixed, is deterministic, you just have to, you have encoded all the randomness in your function phi. Okay. So the point is that you want to know the law of your function phi. The question is, determine the law of phi, given the fact that you know that all the randomness is in phi. Okay, so physicists claim, well, they have some pretty much convincing heuristics, which say that phi is a UVL field. I'm going to explain a bit what it is, but say that this this description of the law of phi is non-rigorous, and this is why you have two ways of proving this statement. The first way to see this is that well, in the continuum, and I am not going to discuss that much this way, but and you can also try to, when you have some complicated problem, you can try to discretize your problem, okay? And if you try to do so, you will get the random planar maps approach. Okay, so what I'm going to do now is that, well, just a word about what is this continuum thing. Continuum. In the continuum, the law of your function phi will be described by, once again, some action. Okay? So the action is the following. H of phi is equal to 1 over 4 pi well, this is here the gradient is in the metric G that you want to consider. Well, this is some action on functions, but if you look at the minimum of this action, I mean, in the same way that you want to see around which point your probability distribution is concentrated, okay? Here you will have the following equation. Well, more or less, this is related to this equation. Say U. Okay. Well, whatever this equation is, this is called the Liouville equation, and this is the equation for the uniformization of surfaces. Because if you take then the metric G, say tilde, is equal to this. Here you have solved your equation in some metric G, okay, and this gives you a solution U, okay, and if you then construct the metric which is conformally equivalent to G up to the factor here, you get a metric with constant curvature. Okay, so this is the equation for the uniformization of surface, and this is well known in Riemann geometry. Okay, so you have some surface with constant curvature. Okay, and your random function here, whatever the way you construct correctly this probability distribution on random function, it is concentrated around this solution here. Okay, this is just a randomization of this equation. Okay. So this is a geometrical approach, and what I'm going to do now is rather to explain you when you condition this guy to being something, you will get some Gaussian multiplicative curve. So let us assume that you can construct such a phi such a random phi, so that you get a metric of this type. If you are on the sphere, there is a nice metric on the sphere. You can take it to be like this. Because, so you take x in R2, and you map the sphere onto the plane. Okay, you take the sphere with the weight. Yes.
Sorry, what is the Q in the?
Yes, this is a parameter. It depends on gamma, and so I can give you the exact expression, but as I won't explain why. I'm not sure.
The gamma and the Q don't appear in the Uval equation afterwards?
No, because I made some transformation here on the parameters. I mean, U is equal to more or less to gamma phi. Okay, so there is some renormalization here. And if you want the correct expression for Q, this is 2 over gamma plus gamma over 2. But, okay. I don't think, yes?
So phi is a real function?
No, not really, because you want it to be a nice function, but actually, when you construct your random function, it will be very bad. As bad as the GFF can be. Okay, so this is a function in h minus epsilon. Okay, so this is a bad function, but I just want you to have the picture. I don't that much. Well, but obviously, phi is bad. Okay.
I mean, I don't see how can you get all the matrix by multiplying one matrix with real numbers, because there are priori there is
here why I claim that all the metrics are conformally equivalent to this one.
Is your metric just on the conformal class of G hat or on all the metrics?
All the metrics on the sphere, you can write them like this up to a diffeomorphism. Because
on the sphere, but on other surfaces?
No, on the other Riemann surfaces, it's more complicated. The sphere is very simple for that reason. Because when you have a metric on the sphere, you can uniformize it with this equation here, and it tells you that you have a conformal map of your surface toward the sphere, and which take on this form. So basically, this is a consequence of the uniformization theorem. So. Well, this is called the round metric. So this is just, you take the uniform metric on the sphere, you send it onto the plane with a conformal map, okay, and you get this round metric on the plane. This is equivalent. You work on the sphere or you work on the plane with this metric, okay? And you can check that this metric has a Ricci scalar curvature too. Okay. Okay, so well, so if you consider now a random measure well, the volume form of this metric is just 4 over the factor times the Lebesgue measure. Okay. So now, if you want to construct, what I'm going to explain is that just admit for a moment that we can construct this measure here. I want to condition it on having volume 1. Okay, and this. So now I'm going to explain how to construct the unit volume Uval measure. Okay, this is this abstract measure. I haven't told you much more on this, but a lot on this. But let's say that we can condition it on having volume 1, and I'm going to explain what it looks like. So No, this is the bridge with Gaussian multiplicative chaos. So you take G, a GFF on the sphere. So what it is? It is a Gaussian. Well, this is pretty much in the same way you construct the GFF with Dirichlet boundary condition, except that now you change the green function. The green function will be the green function of the Laplacian on the sphere with vanishing mean. There's 2 pi f, and you require your solution to have a 0 mean. Okay. So if you look at this Laplacian equation, okay, you can apply the diagonalization theorem and get. Well, you can expand your green function in terms of the eigenvalues of the Laplacian. Okay, so you get an expansion of the GFF in terms of eigenfunctions of the Laplacian. Okay, and you get the same decomposition as you get for the Dirichlet boundary GFF. Okay, this is pretty much in the same way. So maybe I don't remember exactly the exact form of this green function, but it's not that bad. So once you've done this, you can construct the GMC, say, take a gamma, okay, you can construct this Gaussian multiplicative chaos, okay, because you have when you expand your GFF along the eigenfunction, you do it in the same way as for the Dirichlet boundary GFF. You expand it along the eigenfunction, you get a decomposition à la Kahn, and so you can construct the Gaussian multiplicative chaos with respect to this GFF, but you take the Radon measure instead of having the Lebesgue measure. You just take the volume form of your round metric. Okay. Well, now I'm going to take 3 points, and you will see in the connection with random planar maps why we take 3 points. Okay. x1, x2, and x3 on R2, say. And you are going to, you define this random measure. So now, maybe, so this is the green function of your Laplacian, okay? So what is this function here when x is close to y? It's close to y. Whatever this green function is, you know that at short scale, it is more or less a log, okay? It's a log up to a smooth function, okay? So if you look at this singularity here, because you have a singularity at each xi. If you look at the shape of this singularity, you get something like this. Sorry, there is a square here. Yeah, there is a square here. So you get this singularity. I'm just want to check with you, following my lecture, why this function is, because it's not clear that this function, which has a singularity, is integrable with respect to this one. Okay. So I want to check this with you. So you have if you are close to xy here you have a singularity of this type, and you want to know if this measure can integrate this singularity. Okay. So recall that I told you that if you look at this measure, call it m gamma, I told you that the decay of balls, when I fix the point that I choose, behave like this. What? Okay. So the thing is, when does a measure with this type of regularity at xi can integrate? When does this type of measure integrate this singularity here? Okay. So obviously, this is true if gamma square is less than 2 gamma square over 2. Well, and you can check that satisfied if gamma less than 2. Okay. So, as we have a gamma, well, the gamma here, well, and this is something we will assume all along. Okay, and furthermore, recall that the Gaussian multiplicative chaos I defined up there, I forgot to mention that if you recall the lecture, it is defined, so we are in dimension 2, it is defined only if and only if gamma square is less than 2 times the dimension. Okay, so dimension is 2, so you must have gamma square less than 4, so gamma is less than 2. Okay, so this is this square root. So this random measure z0 is well defined. Okay, so now I'm going to define the Jouville measure, and it's going to be, well, say z of Borel set A I'm going to define the law of this random variable here. So I have to take all the suitable functional f defined on R. And I'm going to give you this expectation here. This is just the expectation of f. So, well, the expectation under which your x is a GFF on the sphere. So there is 3 minus well, divided by a constant to normalize this expectation to be 1 when f is equal to 1. Okay, so z is just the expectation of this fraction here. Okay. So this is a law which depends on the xi, okay, and gamma. Okay, this is the unit volume you will measure. And if you take, A, your set A equal to R2, okay, you see that here you've got 1. Okay, so this is a unit volume measure. And here you may say, why? Well, is it sure that this random variable here is integrable? Because you have a 1 over something, it's not sure that this expectation is finite. But remember, I told you that Gaussian multiplicative chaos has negative moments. Okay, so here you have something which is positive, and so you are just left with computing the negative moments of some Gaussian multiplicative chaos, and it is finite. Okay, so now what is the connection with random parallel maps? Yes.
The normalization is not Z, it's a constant, right?
Because yes, this is constant. Well, that's n like normalization. Okay. Do we have questions on the construction? Okay, so well, actually, you can see as an exercise that if you take a conformal map of the sphere, okay, and you can check the following thing. If you take so the conformal maps on the sphere are just the Möbius transformation. Okay, so you change your 3 points, and you apply a phi to this measure, to this definition, and you look at f of psi of a. Okay, you may wonder what happens to this measure when, sorry, there is a z missing here. Z of the set psi of a, and you will see that this is exactly the same measure. Okay. Right, so in a way it is conformally invariant. So now connection with random planar maps. So the thing is that to see, well, it's not really clear. I mean, mathematically, why all this quantum gravity stuff yields gives you this measure in the end. Okay, so physicists have developed another approach, which is the approach of the random planar maps. In a way, if you look at your action, your Einstein-Hilbert action, you want to discretize your metric. Okay, to have a finite number of metric, and then play with them. Okay, with the Einstein-Hilbert action, to weight them properly, to give a nice probability distribution on this random matrix with a finite amount of them. And you want to take the scaling limit of this discretized metric to get something in the end that you expect to be this kind of things. Okay. So this is a discrete approach of the same problem, and well, you expect to have something well, which is very close. So the thing is that you take, well, I will play with the triangulation of the sphere. So you know that this is a combinatorial object, where you have a combinatorial way of gluing some triangles. Yes. So the thing is that if you want to do UV quantum gravity, you are not that much interested in the topology of this object, rather in their conformal structure. Okay. So the thing is, I'm going to explain roughly how to construct a conformal structure on this thing. So you have all your triangles, and you will see, well, this is a combinatorial shape of equilateral of triangles. Okay, and now you want to glue them so as to get conformal structure. So how do you do this? See each face as an equilateral triangle. Okay, with say volume 1. Well, this is very much an equilateral triangle in the plane, and you make sure that it has volume 1 for the Lebesgue measure. Yes, Lebesgue measure. Okay. Or if you want, you can say that each edge has length 1. Okay. It's not equivalent to saying, of course, that it has volume 1, but you have to fix the volume of your triangle, and I fix it to have volume 1. So now, how do you glue your triangle in order to have a conformal structure? You know that to have a conformal structure, you have to construct charts which are biholomorphic. Okay. So assume that. So if you want to glue, if you take a point inside a face, how do you construct the conformal chart? You just take a small ball inside your triangle, and you just take the identity map. Okay, you just take the identity map to C. Okay. This is a chart for a point inside the triangle. Okay. So now, if you have a point in the interior of an edge, here you glue your triangle like this, and you take a ball here, and you just take the identity map to C. Okay. So this configuration are not really a problem, okay? Because you can glue your triangles, no problem. Okay. This is kind of intuitive. Well, the thing is that the problem occurs when you are at the vertex of your triangulation. So say for instance that you want to glue well, say first the simple example. You are at a vertex, but you have 6 triangles. Okay, this is very simple. When you have 6 triangles, this is a good configuration. Okay, you glue them like this. Okay, and so you are here, and you want to construct a conformal chart here. Okay, so you take the ball here, and you just take the identity map into C. Okay, the problem is that when you are at a vertex and you have more or less than 6 equilateral triangles. Okay, so how do you do this? For instance, let's take 3. So you have 3 triangles. You take the map 6/3, so that you will distort your triangle in order that they have twice their angles. Okay, so you have now big triangles. This map takes your triangle into this configuration here. So you can okay, you take a ball. You are at the vertex here. Okay, so you take a ball. You just apply this transformation to this triangle, and you glue it here. You take this triangle here. You multiply the angles by 2. Okay, and glue it here, and the same strategy for the last one. Okay, so you get a chart. And so if you want to glue three triangles, you have to apply this chart so that you multiply the angle by 2, and then you can glue them together. Okay. So the thing is that in the end, when you have G triangles, you just apply the chart z of 6 over g for drawing G triangles. Okay. And if you do so, you can check that the charts you have are biholomorphic. Okay. So in the end, you get a conformal structure on a triangulation G. Okay.
Why isn't there a problem? I mean, so say in the case of 3 triangles, you're looking at the map z squared, so the inverse is a square root. Why isn't there a problem?
Why is there?
Why is there not a problem? Because the inverse, you know, the square root is not exactly.
Why is because well, this is the. I don't understand your question. Why you say why is that not a problem for coming back?
Yes.
Because this chart gives you the conformal structure here. You don't have to check that this map is something. You have to check that the composition of 2 maps are holomorphic. I mean, take any the most weird surface you want, which is just topologically equivalent to the sphere, say, and say that take this map as a. For instance, take this map. You have an homomorphism from your very bad surface onto the sphere, and you equip your very bad surface. I mean, when you look at it, it's very bad, but you say that this gives you say a chart for giving to your surface C infinity to be a C infinity manifold. Okay, but you can have a C infinity manifold on something which is very bad. This is not because your eyes tells you that the surface is bad, that your charts don't tell you the converse. Okay. Well, I don't know if it's clear, but.
Okay, I understand. Thank you.
Okay, so the thing is that now. Well, everything. So you have a conformal structure on your triangulation, and the uniformization. So your triangulation has the topology of the sphere. Okay. So the uniformization theorem tells you that there is one conformal map at least, which sends your triangulation with this structure onto the sphere. Okay. But you know that. Well, say if you have a uniformizing map. Okay. You can take a Möbius transformation of the sphere because this is a conformal map of the sphere. You can compose your uniformizing map for your triangulation with another Möbius transform and get another uniformizing map. Okay, so there is a degree of freedom in this embedding of your triangulation onto the sphere. Okay, and we have to set up something to face this degree of freedom. Okay. Because you have all the Möbius transformation that will give you another uniformizing map, and we don't feel at ease with that because there is no canonical way of choosing this uniformizing map. Okay. So now I'm going to consider Tn3 triangulation with n faces. So how do you fix the degree of freedom with respect to Möbius transform? You know that you fix the Möbius one Möbius transform when you fix 3 points and require these 3 points to be sent to 3 another points. Okay, when you fix this, there is no more degree of freedom. So that's why we consider triangulations with n faces and 3 marked faces, or vertex, or vertices if you want. Okay. Won't change the result. Okay. So if you do so, okay. So now if you take a T, take a triangulation T in this set, okay, equip T with a conformal structure. So by the way, I should mention that you can find the details of this construction in a paper by Gill and Rhodes on the, well, they've done this on the UIPQ, PQ, maybe, I don't know. So, but you can also find all the details based on the paper of Gill Rhodes. You can find another, well, the same construction. You can find the details of this glimpse on the conformal structure of something. I don't remember what, but maybe random planar maps, but it's on archive. So you have enough words to Google efficiently, okay, the paper. Conformal structure. Okay, but now you know how to fix the Möbius degree of freedom, because you will require the 3 marked face to be sent to 3 points, okay, x1, x2, and x3. Those points are used in the construction of the unit volume Liouville measure. Okay, so so now you can embed T conformally. So with the uniformization theorem onto the sphere. By sending your 3 faces, which are ordered, by sending the 3 faces or vertices to x1, x2, and x3 used for the Liouville measure. Well, for the Z. Okay. So now you have a way of embedding triangulation of with the topology of the sphere conformally onto the sphere. Okay. What do I want to say now? Oh, okay. Now what I want to do is to construct some discrete volume form on this triangulation. Okay, because this is this discrete volume form, this triangulation, which is likely to converge towards the Liouville measure. Okay. So how do you do this? Well, you just have to put a volume 1 over n on each. What happens? You have glued your triangles. You have glued your equilateral triangles in the way I just described, and you have a conformal map which sends your triangles, say call psi this conformal map, onto some weird objects. Say, I don't know how it may look like, but say something like this. Well, you have some triangles a bit distorted, recovering the sphere. Okay, and you have this conformal map which sends your triangulation, you're gluing onto this object, and in particular, it sends all your triangles onto something which looks like this, okay, a weird face of your sphere. Okay, is it clear? Okay, so now with this conformal map, you can transport the Euclidean metric on this triangle onto a metric here, which is just onto this face here. This is just, you can even have an explicit form here. This is phi minus 1 prime z dz2. Okay? But whatever this metric is on this face, you just say that the total volume here is 1 over n, so you just have to multiply this face by 1 over n, this metric by 1 over n. Okay, so that you have on each face a volume of 1 over n, and this factor here will tell you how the mass is distributed on your weird face here. Okay, but in the end, so now you have a way. So you have put a mass of 1 over n on each face. Okay. So you have n faces, a mass of 1 over n on each face. Okay, so you have, if you look at the volume form you have here, so if you put a mass on each face, you know how to construct a measure on this triangulation on the sphere. And if you look at this volume, the measure you get of the sphere is you have n faces with 1 over n mass, and you should have 1. Okay? Is it clear? Okay, you should have 1. Okay? So there is nothing random on that in that story. This is just about constructing a volume form on the sphere associated to each triangulation. Now I'm going to explain how you randomly sample these triangulations. Well, I should have kept this blackboard, but okay. So now I keep this thing here. So you just take you have some amount of elements in this set. You just take it uniformly at random, okay? Because Tn3 is finite. You know, as in the lecture Gregory gave you, up to orientation preserving homeomorphism. Okay, well, but whatever, you know that this set is finite, and you just take uniformly, just pick uniformly at random. A T belonging to Tn3. Okay. So the conjecture is the following. So maybe. So in fact, the law of this random measure is the following: f of mu n. So you define a random measure on the triangulation, which is given by sum over T divided by the cardinal of T3n. See, you get a random measure this way. This means that if you want to have a random measure, you just take uniformly at random a T, equip it with a conformal structure, construct the corresponding volume form, okay, and just sum over all the possible t's, and you get the law of your, say, call it, just get the law of a random measure on the triangulations. Okay? Yes?
Does this correspond to the case where the beta equals 0?
No. Here, what do you mean by beta is equal to Okay, I see what you. No. This okay, I see why you're asking the question. This corresponds rather to the gx here, because you want to weight this way, okay? Recall that your weight for quantum gravity is this term here, because the Einstein-Hilbert, the integral in the Einstein-Hilbert action, I told you that there is one term which is useless. So you're just left with this expression here. But to simplify the presentation, I condition on having a volume 1. So this term disappears. Okay, so you are not just left with a uniform measure on metrics, and this is why you take the uniform measure here. Okay. And so now the conjecture is. Well, this is a conjecture at the level of a volume form, okay? Because you know that Gregory explained you how to construct a random metric, okay? But the construction of the random metric on this sphere is maybe in process, but Jason have some word about it maybe, but we don't know how to construct the volume form of this object. There have been some progress made by Duplantier, Miller, and Sheffield recently. In the case of pure gravity, this is why this is what I explained you here. Okay, but I just focus on the volume form. You can also, if you want, when you have a metric, there are a lot of objects you can look at. Okay, you can look at the volume form, you can look at the distance, you can look at a Brownian motion. For this model, there are some objects that we can construct, and some other objects that we don't know how to construct. So I'm just focusing on the volume form, which is rather simple to express. So the conjecture is as n goes to infinity. The random measure. The random measure mu n under the probability measure Pn converges in law with respect to the topology of weak convergence. So not vague here, weak convergence towards the unit volume you will measure. Okay, and I give you the value of gamma for gamma equal to square root of 8/3. So the conjecture precisely is this one, but okay, there is something I haven't explained to you. This is why we get square root of 8/3 here, and actually you can see this value on the volume of the random triangulation. Okay, because remember that I conditioned everything to having volume 1. So I have no volume, it is fixed to 1. Okay, but you can, if you don't make this restriction, you can see the value of gamma on the growth of, you can look at the cardinal of this set here and see the correct value of gamma on the growth, the cardinal of this ensemble here. And more generally here, this is called pure gravity because there is no what physicists call interacting matter field. You know that usually we want the gravity to interact with something else, and this something else is called well, matter field in physics. For the purposes of this seminar, this workshop, this is usually a conformal field theory. The matter field is a conformal field theory. You want to couple, so you want to add another term here corresponding to the partition function of some conformal field theory. And in the end, you will get the same conjecture, but with another possible value of gamma. Okay? And you can see the exact value of gamma on the number of triangulation with n faces with the weight on your partition function of triangulation. But as I totally skipped this part in my presentation, I cannot explain how you can see it. And actually, for all the different values of gamma, you get completely different geometry. So they are all of interest, but this is certainly the simpler situation. So in 1 hour, this is all I can do. Okay. Thank you for your attention. Any questions? Oh.
Is there a way to describe the law of this Passé inverse of
Sorry?
the gluing map? Is there a way of describe this law of this gluing map? This phi.
This phi up there?
Yeah.
Does it describe?
The distribution, the law of it.
Ah, the law of it. I don't know. I really don't know what the shape of this map is. I don't know. No idea what it looks like. Should be very bad. At least in the limit. Well, but yes. Well, if you look at this term here, if you look at face, and when you will squeeze the size of your face because of the scaling limit, you are supposed to converge towards something like the exponential of the Liouville field. So locally, it should be the exponential of a Gaussian free field. So you just have the derivative of the inverse map.